results, and then I'll tell you a little bit more about the concept because it helps understand the concept a little better. So these are results from 2 field trials we've conducted over the past year. We went out to Arizona. That's at Black Point near Flagstaff, and this was done in conjunction with MSL. What you're looking at is a 4-wheeled rover, very similar to MER, about the same size, that is actually just driven up a slope about 35 degrees going over rocks. So we think, well, what's the difference? So here's the fundamental difference. This rover actually is made out of 3 separable pieces. The front 2 wheels are a rover in itself, and that's an extreme terrain robot that actually can go over the cliff, and it is tethered to the rest of the system. Now it gets onto the stratigraphic layers and deploys a spectrometer and microscopic imager, turns around, and then takes a thermal measurement. Now each one of these sides you can put up to 4 instruments, so a total of 8 instruments can go in one of these robots. And then it goes down. It's about a 30-degree slope here that you can go explore, come back, and then you redock with the system. Now, redocking is a difficult problem, but the tether really helps you a lot, and then you can go off and to the next area. And then here is about an 80-degree drop for a short period. You go down. You can do simple things like trenching with just rotating one wheel. Take a measurement and do different types of measurement. And this looks more steep, but it's actually 50-degree slope only, and at the top is 80. Now, if you throw this in a very, very rocky terrain, you can high center, and you can see here just it high centers and it backs up because it uses the tether to pull itself out of trouble. If you hit a soft spot at the bottom of a crater, a sand trap, you can pull yourself with the tether. So the tether here plays a very key role. Not only provides you mechanical support, it also provides you power and communication through the tether. When you get into these extreme areas, you cannot guarantee line of sight, you cannot guarantee get into the caves, you may not have access to sunlight. So you want to be able to do these things reliably and with a reliable solution. So what you see here is another field trial we've done in conjunction with the National Geographic. These are steeper slopes, about 65 to 85 degree slopes that you can go up and down, and we did about 200-meter excursions on these. So this rover, we fielded it over 3 days, and we've driven about half a kilometer in these kind of terrains. So I did touch upon a number of the challenges. So if we look at, we're trying to build a mission using a technology like this, and this is by no means the only technology to access extreme terrains. We've seen other different ideas. We have to deal with a number of challenges. One of them is the steep slopes, the uneven terrains. We have to deal with sinkage issues, as well as deal with large obstacles and boulders. There are power and communication challenges because you do have, you may not guarantee constant communication with the platforms. You have to address these, as well as sunlight for energy. And there are other environmental challenges. For the moon in particular is extreme cold. For Mars is the plant reflection forward and backward, capturing these samples, the ice and brine samples, and thermal impacts that your system may have on the environment. So just giving you a little bit more detail about the system that you've just seen. So it is on the same theme that my colleagues touched upon, which is the idea of doing more with less. So this is a 2-wheeled robot that has a tether running through it. And if you think about it, it operates like a yo-yo. It's basically a yo-yo with 4 motors total. Now, one of the key features about this robot, it has 2 large donuts that are inside the wheels, but they move separate from the wheels. And that's where all your instruments go. So you can put a total of 8 science instruments in this. It also has similar capabilities like the stereoscopic cameras here. It has an arm just to where the tether runs through. This can operate with and without the tether. It does have the large wheel, so it's able to go over obstacles about a wheel radius. And it can operate upside down. You get into extreme areas, you can never guarantee that you're not going to flip. And experience has shown that when you field these rovers, there is a probability that's not zero that you will flip over. Now, the way these science, so the main thing, our scientist Pam Conrad has actually termed this thing the mobile science toolkit, because you're actually carrying a suite of science instruments on this platform. Now, if you look in terms of the mass, the mass and volume of instruments you can put relative to the mobility system is very favorable, where you can get a much higher science payload on these. The kind of, you can put spectrometers in this, XRD, XRF, Mossbauer, infrared spectrometers. You can also put microscopic imagers. We heard about the multispectral imager that Glenn Seller has another abstract that we'll be presenting on. You can do also context structural 3D reconstruction of the terrain. And also right now we're working with Honeybee to look at scoring, as well as we've done scooping in the past, and then we'll be looking at scoring, sample handling, and sample transfer. This is a deployed science module, and we have two instruments here. We have the reflection spectrometer as well as a microscopic imager for the field test that we've done. Now, one of the things, well, how do you get to the extreme terrain areas? That's a very important thing, and it's very coupled to landing. So if you actually take the same idea of this two-wheeled robot, if you put two of them, now you do have the element of redundancy. Either one can go into the extreme terrain, and you create a central module that brings them two together. Then you do have a Mir-like rover that has three pieces that each can operate separately. And you can also do network science by deploying the two axles out far away from the central module. This gives you redundancy, modularity, reliability, and affordability. Now, in terms of mission concepts, you can do a lot of leverage. You can leverage Mir or other Phoenix launch and cruise stages. You can do EDL, landing in the vicinity of the crater. You can align your ellipse in a way that allows you to traverse only several kilometers before you reach the extreme terrain. You can use a lot of heritage avionics and sensors power systems, and then you just deploy a separate type of mobility that can get you into the extreme terrains. And then once you capture, you can do the in-situ science, you can collect the samples, and you can do you can analyze these samples in the central module up on top of the cliff, or you can put them in canisters and deploy them on the ground for sample return. You can look at this as ways to combine it with different types of mission. You can put it on the lander, which requires a long tether if you're trying to get into some of the extreme areas. You can put it in this dual axle configuration or on a larger rover. Let me just go through a summary here. So basically what I shared with you here is that a new surface capability could enable us to have a higher science return at an affordable cost. I just want to point out that extreme terrain mobility was one of the top 8 ranked new technology development priorities recommended by the National Research Council. Also, having this capability will enable us to do a sample return from the water seeps, which is to some scientists scientifically compelling, as well as it has relevance not only to Mars, it has relevance to the Moon, as well as the SMD and the human program. And we've shown through our field test results that such an approach could be doable within the time frame of a 2018, possibly 2020 mission. And the designs that we looked at it in the context of a path to flight. And we do not believe there are major showstoppers. There are challenges, but no major showstoppers. Thank you very much. I would like to acknowledge the team of students and JPL employees who work on it from JPL Contact. Also, just a note to mention there were 2 other people who proposed very similar concepts, Hobby Price and Stephen Edberg. Stephen looked at proposing caves, exploring caves using a very similar platform, and Hobby Price from JPL also proposed sampling from water seeps. And we've worked together with Hobby to put this together. Thank you very much.